12 noon here, so good morning, afternoon, or evening, depending on where you are. And welcome to the last IPEC talk for this summer. And Peter Brandon will be continuing his stellar series here on Lorentzian polynomials. Go ahead, Peter.
Thank you. So since I want to cover this work with Jonathan Leake, I'm not going to do all details today, but I will still try to give you a feeling of the proof and what's going on. But then there are some technical details which I will skip. So let us recall what we started to do last time. So our goal is to define a multivariate polynomial, which we call pol. And they are indexed by two flats where, well, it's very confusing what are defined here. So for each pair of flats k smaller than L, in the lattice of flats of a matroid, we'll define this polynomial, multivariate polynomial, indexed by the flats that sit between k and L. So this is our goal. And this is the lattice of flats. In M. Okay. So we started to define this last time. And so this polynomial is indexed by variables which are, well, it's a polynomial in variables indexed by sets. So we let this EKL be this Euclidean space that are of variables indexed by sets, and it's of dimension 2 to the power L minus k minus 2. So inside this space sits the subspace of modular functions or elements. So these are just these set functions that satisfies the modular law, right? And by convention, since in this subspace we have strict inclusions here, so we're not considering the endpoints k and l here. So, but for this equation to hold, we set yk and yl to be 0 outside.
Error. In the past, you used inequality, but you have equality now, right?
Did I say inequality?
Maybe not defining modular elements, but you use this type of inequality comparison before.
Yeah, I will define submodular, which is
okay.
You know, by inequality. But so it's easy to see that these modular elements are just described by sort of, well, they are given by this sum of variables where we have real numbers xi for each I in L take away k. So then y is modular if and only if there are such numbers xi, so that ys is the sum of all i's in S take away k, where this sum of all the variables in L minus k is 0. And this is not hard to see. And now, as Teddy said, we want to look at the submodular elements. So we want a cone for this polynomial to be Lorentzian with respect to. So, and this convex cone is the cone of strictly submodular elements. And they are defined by this modular law, which should hold strictly. And in order for it to hold strictly, of course, S and T must be incomparable, because if they're incomparable, then this is, well, this is equal to this. So that since it's defined by strict inequalities, it's an open cone. And we recall this, what the linearity space of a convex cone is. Well, it's the largest linear space contained in the closure. And another way of phrasing this, it's that it is the intersection of the closure of C with its negative. And now it's not hard to see that, well, of course, these lie on the in the boundary of C, so, and it's not hard to see that this is actually these modular elements is the linearity space of this cone of strictly submodular elements. Now we have this notion which we borrow from Hodge theory, that a convex cone, we call it effective if this weird relation looks is satisfied. Well, what it says is that for any element in your cone, you can always add something in its linearity space so that you come into the positive orthant. And this should say we should have, no, this is true. Okay. So an obvious example of this is for the upper half plane. So if we take some, if we take any vector here, here it points in the second quadrant, then of course we can take, for example, this and then add some negative x to it and get there. So in symbols, we can take, for example, 1, y, which is in the positive orthant, plus x minus 1, 0. So this is an example of an effective cone. And indeed, it's a sort of folklore theorem that this cone of strictly submodular functions is effective. So this means then, as I said, that if we have so modulo the linearity space, we can view this as living in the positive orthant. So we can, for any element in this cone, we can add something we can add some modular element, so we point in the positive orthant. So all the coordinates are positive. And now, since we have these polynomials which are defined for pairs of comparable flats, we want to do some induction. So if we have K and L, we want to be able to restrict to a smaller interval. And this is done by sort of a canonical projection, which is not very important at this stage to how it actually looks like. It's the properties that are important. But you see, if we would consider the whole interval, then these functions here would be typical modular elements. So they sort of what this projection does, it of course restricts to this interval, but then it modifies by some modular elements so that these coordinates yf and yg are sort of 0. And since these are modular elements, it's not hard to see that these projections, they map the submodular cones to the submodular cones of the smaller interval. And because it does that, then it also maps the linearity spaces. So it maps the modular elements to the modular elements again. So it's not that important to see what these projections are actually, which ones they are, but or how they look like, but that these properties are important. That they map these submodular cones to the submodular cones and the modular to modular. And they also have this, they also commute because they are sort of proper projections. Okay, so now we come to the definition of these polynomials. So we have shorthand DKL for the rank of L minus the rank of K minus 1. And this DKL will be the degree of the polynomials. So now we define these polynomials recursively. So we do it first for covering relations. And this is when DKL is 0. So the rank of L and the rank of K differs by 1. So if we have that, then we just define this polynomial to be simply 1. And otherwise, if this DKL is greater or equal to 1, so if K and L are not adjacent in the Hasse diagram, then we have this recursive definition. So on the right-hand side, we have the polynomial we want to express, and we express it as a sum of then smaller polynomials for smaller intervals. Here. So this is a recursive definition, and here these projections come in. Yeah. So these projections take T in this EKL to EKF. So this is why this makes sense, so to speak. So this is, we'll return to this defining equation several times. But for example, by induction, it's not hard to see, sort of, since we divide this polynomial, the support of this polynomial is going to be the support of the union of the support of TF times the support of this times the support of this. And since we've sort of divided the intervals here, it's not hard to see that the support of the polynomial are going to be monomials of chains in the lattice of flats. But it's not, it's sort of, since we have, if we recall, we have negatives here in the projections. So we will not in general have, so we in general have negative coefficients coming up when we expand these polynomials. And also by induction, one can see that the degree of the polynomial is going to be this DKL, just by additivity here. So let us see, well, let us apply this to, if DKL is equal to 1, well, then the lattice of flats looks something like this. Right? So the rank of L and K should differ by 2 now. So we have K here, L here, and then we have some sort of flats in the middle. So this is the only way it can look like. And now then DKL is 1, so we have 1 here. And then we have, so then we've divided, so these F's here, they lie just in the middle here. So the polynomial for this is going to be 1, and the polynomial for this is going to be 1. So all of these terms here, this is going to be 1, and this is going to be 1. So for if DKL is 1, then we will just get the sum of the flats in between K and L.
Peter?
Yep.
Perhaps after multiplying the polynomial by DKL, the right-hand side, is it always integer? It's integer coefficients, right? Positive.
Yeah. It follows that it's going to have integer coefficients.
Yeah.
Well,
beside DKL.
yeah, it will follow. It will follow later that it will indeed have integer coefficients. But from the definition, it just follows that it has. Well, no, it doesn't have. I don't think it's going to have actually. Well, if you divide by DKL factorial, I guess. If you multiply by this. Well, so let us still be in the case. We're still in the case where DKL is equal to 1, and we want to look at sort of. We want to see some features of some features of these linear polynomials. So since this is a lattice of flats, well, each interval is also a lattice of flats. So these F1 to Fm will just be the parallel classes. So these F1 through Fm, if we take F1 take away k and Fm take away k, these will partition L take away k, because this is a lattice of flats. So these are the sort of parallel classes here. So, and recall that any vector in any modular element could be written as a sum of xi's, where the sum of xi, the whole sum of xi is 0. So if we evaluate this linear polynomial at w, and we recall that this was the definition, this was how it looks like for linear ones, well, we plug in this sum of the xi's, but since these partition L minus k, we'll just get the sum of the whole thing, which is that 0 by definition. So from this follows that the polynomial is invariant under adding things in the modular space, since this is a linear polynomial. And again, since CKL is effective now, we may always add some modular element so that all coefficients are positive. So it follows then that we can assume that when evaluating at some t, we can assume that all the, well, some t in the submodular cone, we can assume that all the entries in t are positive. So this means that, well, the polynomial evaluates to something positive when v is in the strict submodular cone. So this was just the linear case, but it happens that this will be a feature of the polynomial for any degree. Now, talk about this soon. So recall now this Euler's formula. So this says that if we have a homogeneous polynomial of degree d, then we may write d times f as the sum xi partial derivative with respect to I, f. And this is sort of simple. And if we then look at this defining polynomial, well, we have the degree here, we have the polynomial here, we have the variables here. So it suggests that this thing here is actually going to be the derivative of the polynomial itself. If we compare this definition with Euler's formula. And indeed, this is the case. So this is sort of the most important feature of these polynomials is that if we differentiate with respect to some flat in between k and l, then we actually get a product of two polynomials, which are products of two polynomials of the same kind, but which for smaller intervals. And this is this feature that enables us to prove the Lorentzian property by induction using this Boschner method. And we could actually use this to define the polynomials too, but it's unclear that it's well defined. But uniquely, this formula uniquely defines the polynomial by Euler's, this Euler's formula. But in order for, yeah, but if we would have this as a definition, we would, you know, we would have to show that it's well defined. But from now on, we can actually use this as the definition of the polynomial. And indeed, just as for linear polynomials, we do have this, that these polynomials are invariant by shifting the variables by some elements in the modular code. So what does this mean? Well, this means that we can always assume by this by the effectiveness, we can always assume that these all the entries are positive, well, for any v in CKL when we want to evaluate this polynomial. Okay. So this is another important property. So one way of phrasing this is also that this polynomial is a polynomial on the quotient space of this and this, right? So now, recall we had two definitions of, in order to be C Lorentzian, we had two definitions. This was the first definition of being C Lorentzian. And the other definition, the other one was that the Hessian had exactly one positive eigenvalue. But now, well, we start instead by using the above two lemmas. One can prove that then all these mixed derivatives are positive, and also using this, well, one can then prove that this Hessian is regular, meaning that the non-zero, well, the off-diagonal non-zero entries, they are connected. And this connectedness, well, this follows from, so this regularity follows from semi-modularity of the lattice. So all geometric lattices are semi-modular. So this, and the Hasse diagram of any semi-modular lattice is connected. Okay. So this is the sort of the theorem that we use to prove C Lorentzianness for effective cones, for polynomials on effective cones. So this, what it says is that if we have some homogeneous polynomial of degree d, and now again d is greater or equal to 3, which was also the case in this Bochner method lemma. And if we now have an effective cone, meaning that we can always translate. So if we have any element in the cone, we can always translate with a vector in the linearity space, so all the coordinates are positive. So if we have so we have an effective cone and a homogeneous polynomial of degree d, and if these three conditions are satisfied, then we can actually deduce that f is C Lorentzian. So the first one is this positivity of the coefficients of the mixed derivatives, which we have now. We have this lemma that tells us that this is the case. And the second one is that the Hessian is indeed regular, and which we also have. And the third one is sort of the induction, which enables us to use induction, and it is that the derivatives in the coordinate directions are C Lorentzian for all I. If we have these three properties, then F is C-Lorentzian. And this is actually just a corollary of this Bochner method lemma. And if you recall, these conditions are quite reminiscent of that too. It said something about the Hessians. If you know the Hessians of the derivatives, if they are if they have exactly one positive eigenvalue, and if the Hessian of the polynomial itself is regular, then actually the Hessian also has just one, exactly one positive eigenvalue. So one can use Bochner method lemma to prove this lemma. And using this, we now see how this main theorem follows, that this polynomial is indeed Lorentzian with respect to the strictly submodular code. So these properties 1 and 2, that the positivity of the mixed derivatives and that the Hessian is regular, is this lemma that I talked about earlier. So these are satisfied. So the proof is now by induction over this degree, and when the degree is greater or equal to 2. And we actually start by we prove the case when d is equal to 2 last, but we now prove the induction step. So what do we have? Well, we have this formula for the derivatives, which were, so we want to use this third property. So we want to deduce by induction that these derivatives are C-Lorentzian. So this is our goal. So we want to use, so we want to prove by induction that the derivatives are C-Lorentzian, and for this we use this formula for the derivatives, and the formula says that it's a product of two polynomials of the same kind. So these polynomials, since they are of smaller degree, they are themselves C-Lorentzian by induction, if we can prove the case of d equals 2, but we postpone that a bit. So these two polynomials are Lorentzian by induction, but since we have this property that these projections, this projection maps into the cone for which this is Lorentzian. So this means that that these polynomials themselves are actually CLK Lorentzian by induction. So these two polynomials are CLK Lorentzian. And we,
Peter,
yes,
the formula you highlighted there to get the derivative being a product of 2 respecting the 3 objects K, L, F. Now, if I want to do 2 derivatives, then does it behave the same?
Yes, actually it does, because we had this property of the projections. They commute. So we will get 2 projections here. If we do, we will get a product of 3 things, right? And we will get a product of projections. But since these projections commute, we will actually, we will get sort of the obvious generalization of this.
Thank you.
Yes. But now we also have this nice property that C-Lorentzian polynomials are closed under products. So since this is C Lorentzian, CLK Lorentzian, and this is CLK Lorentzian, then this product is CLK Lorentzian. So indeed, we have this third property by induction. So this is sort of how the proof works. So this third property follows. So for the induction proof to go through, we just have to consider the case when the degree is equal to 2. So for quadratics. Okay. And well, so this is probably not a lattice or flat, but this for the degree 2, then the rank of K and L should differ by 3. So this is the case here. So we have sort of 2 non-trivial layers here, and we call these the first layer F. The elements here, we call them F, and the elements here, we call them G. And then one can use this recursion to actually compute a closed formula for it. And it reads as follows. So first we have just a square of the sum of the flats in the first layer. And then we have when we subtract off a bunch of squares, one for each G, one for each G in the second layer, and they are of this form. And just from looking at this, we see that this has the right signature. Well, one way of seeing it is by this Cauchy interlacing. So if we look at this, so what do I mean by that? So see that maybe I should give some more details here why this is true. Just move this down. So if we look at the we see that this pol KL of T is a negative semi-definite on this on the hyperplane where we sum over all these F's in the first layer here. And this is simply because, well, in this hyperplane, well, this is 0, so the polynomial evaluates to something non-positive. So then by this Cauchy interlacing, the Hessian, well, it has at most one positive eigenvalue. Because it says that this Cauchy interlacing says that the eigenvalues of the polynomial itself should interlace something, this Hessian of the restricted one, which has only non-positive eigenvalues. So it can have at most one positive eigenvalue by interlacing. But we know from before that that the polynomial evaluates to something positive for vectors in the strict submodular cone. And why is this? Well, because we have this mixed because, well, one way of seeing this is that this is equal to I guess 1 over d factorial db if we take it d times f. So this is positive by this, since the mixed derivatives are always positive. So this sort of concludes the proof. So the degree 2 is the degree 2 case is just by a direct computation, which sort of follows from working with this recursive formula. So how does the Heron-Walter-Welsch conjecture follow? Well, we apply this to, well, we can assume that we have no loops because the characteristic polynomial is the same for the matroids where we throw away all the loops. So we assume that we have no loops, and we then take K to be the empty set and L to be the whole ground set. And then we look at some specified elements alpha and beta in the closure of the submodular cone. And they are defined by take the cardinality of S and the cardinality of S and then normalized by the cardinality of E, and then take the complement of the cardinality of S and normalized by E. And why are these submodular? Well, if we look at these vectors, this vector, for example, on the whole, well, on all subsets of E, so where we have also these, where we allow for equality, then this is a typical modular element, right? So all the all these submodular inequalities hold with equality. So we're just left with the case when when these submodular inequalities involve the empty set or the full set, but then since we have zeros at the top, then we will have actually something positive for these submodular inequalities which involve the empty set and the full set. So these are, it's not hard to see that these are actually in the closure of the submodular cone. And then we sort of follow this strategy of, so if we have some Lorentzians or C-Lorentzian polynomial, and if we then restrict to 2 vectors in the cone or in the closure of the cone, and expand these, so this will, yeah, and expand this in its Taylor coefficients, then these Taylor coefficients by this Alexandrov-Frenkel inequalities, they will be ultra log concave. So by C-Lorentzian, the C-Lorentzian property for a multivariate polynomial, we will get ultra log concavity of these coefficients here. And indeed, a combinatorial reasoning using this recursion actually shows that this AK here is the kth coefficient of this unsigned characteristic polynomial. So these So recall, maybe I write this here. So chi m of t are these wi with sign -1 to the r minus I believe, t to the r minus I. So one can deduce that these polynomials here are actually this unsigned characteristic polynomial divided by 1 plus t. And from this follows, well, a property of, since log concavity of polynomials is closed under products, this means that this is log concave too. Since, well, maybe so this. So
Peter, are the W case positive and the A case positive?
yeah. So this is one feature of being, since these vectors alpha and beta are in the cone, then these coefficients here are going to be mixed derivatives if you expand this. So, and mixed derivatives are always positive, but since these are in the closed cones, then it will only give non-negativity, but these are going to be positive indeed.
Okay.
So, and recall that, well, since if we call this f of t, so these coefficients of f, these coefficients of f of t are going to be log concave by this property, and one feature of, we know that if the coefficients, if f of t has log concave coefficients, and so g of t has log concave coefficients, then f of t times g of t has log concave coefficients. I guess you also need that it has no internal zeros, but these do not. This is a classical sort of result. So then if we multiply this polynomial f of, so this polynomial here is f of t times 1 plus t, and 1 plus t has log concave coefficients too. So this tells us that this polynomial indeed has log concave coefficients. And as I told you before, this Alexandrov-Frenkel inequalities implies that the sequence AK is log concave, since these coefficients here are these mixed derivatives. And then we get from this, we get that this Whitney numbers of the second kind or of the first kind are log concave. And I guess this is the proof. And I thought I would not have as much time as I did, but since I wrote up everything before then, I finished, I guess, a quarter earlier. But I'd be happy to expand on parts or answer questions or dig deeper into it if you want.
Okay, great, Peter. That's really great. Just, I mean, on behalf of the audience, like to thank you. It's really great to see the details of this kind of amazing method for proving log concavity conjectures. Oh yeah, so any questions for Petter? Until someone thinks, oh, go ahead.
Yeah, I should say that the details of, so what I left, yeah, the details I guess are in these two lemmas, but these are in this in a recent preprint by Jonathan Leake and myself, and it's on the archive if you want to look at the details. And I guess if you sort of saw the details of this that I gave for the theory of C. Lorentzian polynomials, it's not too hard to go through.
Okay.
Yep.
By the way, I wanted to mention that there seems to be some support from Anna and some others for doing IPAC again next year. So at least tentatively, we're planning on that. See, Bruce seems to be positive. So yeah, we were really treated to some gems here this summer with Michelle and John's paper, and then this one here. Okay, I guess there's no questions. So we'll thank Petter again, and have a great summer, everyone. And
excuse me?
Yes, go ahead.
May I ask a question about the last lecture?
Absolutely.
Last one.
The previous one.
Yeah, the previous one. Yeah.
Yeah.
So it's
Do you want me to put up the slides? Or?
Yeah, it would be better. So it's about a proof of the independence polynomial is Lorentzian.
Yes.
And
Oh,
I think it's still below this one, like at the proof.
Oh yeah.
Yeah, this one. And can you still go down a little bit? Yeah, and still down a little bit. Yes. Oh yeah, here. Yeah, so here, like, we want to prove this quadratic polynomial is stable, but like which characterization are you using here? Because like it looks like you're looking at, so you're looking, if you so the result you get is like you look at, if you view the polynomial as quadratic for x0, and you're saying that it's real rooted, so you use the discriminant, and that's how you get the things below, right?
Well, what I actually do is maybe I could. So we have these, I guess, 4 equivalent conditions.
Yeah.
Yeah. So oh, let me try to.
That's for the polynomial in the form of like xtax, right?
Yeah, I'll try. So we had these. So if we had a polynomial of this form, right?
Yeah.
And then one of these equivalent statements says that if say if E is now one of the, E is some vector in Rn such that E transpose AE is greater than 0.
Yeah.
And this, then we should have this statement that E transpose AX squared is greater or equal to E transpose A E times X transpose AX, right?
Yeah. Yep.
And in the proof above, use then one uses E to be this coordinate vector just in direction of X naught.
Oh.
So yeah, so what do we call this? Well, this is just the 1 0.
Yeah.
0. Because then this is exactly, then what you get is this discriminant here between these.
Okay.
So I was a bit quick there.
And the X is the like 0, 1, 1, 1, 1, right? Like 0 and then OR1.
Pardon?
So the X is like
X should be for all X in R. And we prove this, yeah, we prove this. And this is what we prove. We prove this for all X in R.
yeah. Yeah, I mean, like the X here is the so it just means the X. Oh, wait a minute. X here means the XE, right? Like O for OE, like X1, X2 to XN.
Yeah, well, X here will be, so this, I guess, this will be the polynomial P of X, and this will just be this entry. This here will be the entry, this entry.
Yeah.
And this here will be the derivative with respect to X naught, so it's going to be this entry.
Okay. Okay, so thank you. Yeah.
So yeah, so sorry, I maybe swept that under the carpet a bit, but it's nice that you wanted details. Thanks.
Okay, by the way, I'd forgotten that Teddy mentioned before today that he had some conjectures, like 5 minutes of conjectures to discuss based on this lecture series. So if you want to, you can hang around and listen to Teddy and his conjectures. If not, have a great summer, and we'll see you possibly, hopefully, if not before next May, then next May in IPAC 3. Okay.
So then I stop my screen saving.
Oh yeah, so go ahead then. Go ahead, Teddy. Does he have?
Okay. And thank you, Jim, and Anna, and everybody else for the fine conference this summer, IPAC. And there was something that I was playing around with, and this is about the coefficients of chromatic polynomials. And as we all know, they have been proved to be log concave. And this is quite fitting with Peter's work too on Lorentzian polynomials. So I'd like to bring this up. The background, I mean, the idea here is I want to push this log concavity further. And I'm claiming, actually, the conjecture is simple. I'm saying that these chromatic polynomial coefficients in absolute value, they are infinitely log concave. And for me, the evidence is the following: some basic examples of graphs, like graphs, no vertices, graphs that are trees, the complete graph. These ones are easy check because even by Peter's work, for instance, the complete graph has real roots. Therefore, it's bound to have low concavity infinitely often. And so that's some evidence. But then I tested several things to base this conjecture. I checked a graph when it is a cycle, a bipartite graph, a cyclic ladder graph, signed book graph, as well as many in the list of Birkhoff and Lewis paper. There are many chromatic polynomials listed. So based on that, I'm claiming that the chromatic polynomials are infinitely log concave. So this is just my announcement, but if Peter has something in this, I would like to hear his opinion.
Yeah. So I just try to recall the proof I had for the case of real-rooted polynomials, and then the proof actually went through stable polynomials. So it could be, so sort of, you sort of look at the sum of the quadratic forms that you get from the elementary symmetric polynomials. So you take ek of x squared minus ek minus 1 times ek plus 1. And this is going to be, well, if you also have minus 1 to the k in front, then this is going to be a stable. Oh. Yeah, I guess. I think that, yeah, I think this should be a stable polynomial. So maybe if we just, it could happen that one could do the same proof, but for Lorentzian polynomials instead. But I would have to, I would have to have a look at the proof, or you could sort of see if it follows. I don't know. Well, if there's sort of a way of making, of doing the same for the quadratics you instead get from no, yeah, okay, but there could be something to it. Yeah, could be a route forward, but it's not as simple as I initially sort of thought. It seems to be non-trivial because you have to work with this Lorentzian polynomials with respect to the submodular cone. But it's the same true for the independence polynomials.
I have not tried.
Yeah, I've not thought about infinite log concavity for a while either. So, but this is these are natural questions, of course, and it could be that one, yeah, that the sort of that the available proofs can be tweaked to prove that too. I don't know. It seems more plausible that that it should be if it's true, it should be simpler for the independence polynomials, I guess. Interesting.
Okay, thank you for your feedback, and thank you for the organizers to let me mention this.
Thank you so much for sharing this.
Thanks.
All right, so I will see you guys hopefully next year.
Yep.
Maybe earlier. All right.
See ya.
Thank you.
Thanks.
Thank you.
Thank you. Bye.
Bye.